Hello guys, welcome back to my channel. And in this video, enough with the proofs. Let's get back to good old integration. So today we'll be actually solving one of the problems of open mathematical Olympiad of the Belarusian Russian University. Now I'm not sure about what year this problem um, came in, but I think it was like 2018 or something. But time is insignificant to us. We are mathematicians. So, anyways, as always, let's get started. Okay, so as always, we'll call our problem I, and it's defined as the integral from 0 to 2 pi of e to the cosine of x times cosine of the sine of x. And well, we're not just done as of now. Cosine of 5x dx. Yeah, that's how bad this is. Okay, so how do we actually gang up against this problem? Well, notice that we have an exponential here. There's an exponential here, and remember that there was this formula to convert cosine of some angle into exponentials. So that said, cosine of some angle theta is equal to e to the I theta plus e to the negative I theta over 2. And this actually comes from Euler's famous identity. Okay, so just because we have an exponential here, let's try to convert this cosine into exponential to see if anything can cancel out, or if we notice any patterns. So integral from 0 to 2 pi of e to the cosine of x multiplied with, we have e to the I, and then whatever was inside the argument. Inside the argument, here we assumed like an arbitrary theta, but we have a sine x. Okay, plus e to the negative I, and then again sine x, and don't forget to divide by 2, and we still have the cosine of 5x dx. Now what I'm going to do is I'm going to actually distribute this by opening the bracket, if you want to call that way. So we'll have e to the cosine of x multiplied with e to the I sine of x, and take the 2 outside, the half outside, multiplied with cosine of 5x dx, plus, I'm just writing this in terms of two integrals by linearity, half of integral from 0 to 2 pi of e to the cosine of x times e to the negative I sine of x times cosine of 5x dx. Fair enough. Now what I'm going to do, I'm going to use some exponential properties. So if you have a product of two exponential terms, the arguments or the powers can add up, provided you have a same base. Here the common base is e, so we can do that. So we have cosine of x plus I sine of x, cosine of 5x dx, half integral from 0 to 2 pi e the cosine of x minus I times sine of x times cosine of 5x dx. Now notice, just in this the argument of this exponential, cosine of x plus I sine of x, that's exactly Euler's identity. That's e to the ix. This ix is again to the power of this e that is in the power of this e in the denominator. So it's like a some sort of tetration going on here, but it's e to the I to ix times cosine of 5x dx plus half of integral from 0 to 2 pi, and here cosine of x minus I sine of x is just e to the negative ix. Basically you just substitute a negative x instead of x in e to the ix and you'll get this, and cosine of 5x as it is. Okay, so our integral I basically got split up in these two things, and like like most of my videos we're going to look at them separately. So call this guy I1, call the other guy I2, and let's look at I1 on a fresh page. See you there. Okay, so as previously stated, I1 is actually half of the integral from 0 to 2 pi of e to the ix times cosine of 5x dx. I mean, doesn't the cosine of 5x just seem like super arbitrary over here? Well, it is pretty arbitrary if you ask me, because it doesn't, do anything significant to this problem. But now notice we have e to the ix in the numerator. Why don't we make a substitution? Let uh, w is equal to e to the ix, so that instead of e to the ix we'll have e to the w after this substitution, just for that. And then notice if we take the natural log on both sides, the natural log of w is equal to ix, implying x is equal to natural log of w over I, but 1 over I, if you multiply and divide by I squared is negative 1, so we have negative I times natural log of w, that's x. Okay, and similarly we can find dx, so dx is just negative I over w dw. Okay, so I1 now becomes half of, we'll write the upper and lower bounds in the end, e to the w cosine of x is negative I times natural log of w, and dx is, take the negative I outside, divided by w dw. And when you plug in 0 in place of x here, you have e to the 0, which is of course 1, and e to the uh, 2 pi I. Now w is e to the ix. E to the ix, x is cosine of x plus I sine of x by Euler's formula. Now if you plug in 2 pi here, cosine of 2 pi is 1, cosine of 2 pi is 0. So we have 1 for the upper bound as well. Now if you are like a really good observer, or like a really good calc 1 calc 2 student, you may notice that if we have the upper and lower bounds the same, this should just, this integral should just go to 0, because by the fundamental theorem of calculus, if you have, say, I don't know, f prime of x evaluated from, say, a to a dx, that will just be f of a minus f of a, which will be 0. But now here's the catch, here's the great catch. We are in the complex plane, boys and girls. That's because we introduced this substitution. We introduced the e to the ix, and whenever e to the ix and cosine x plus I sine x are concerned, it's always the complex plane. So it's not like a linear integral. It's not like a straight integral, like have a start point and then the end point is either behind you or ahead of you. It's not this kind of integral, guys. If it were that kind of integral, which is on the real plane, the real uh, domain, then indeed it would go to 0 by the fundamental theorem of calculus. But what this is doing actually, and let me actually give you a slight insight. Okay, so for the insight, I'll need to draw the complex plane. So this is your real axis, this is your imaginary axis. So what's happening is when you have 0, and you get 1, right? E to the 0 is 1, so you have this point on the real axis. Fair enough. But when you do e to the 2 pi I, basically the thing, the unit e to the I x or e to the I theta, let's call it theta, is actually rotating stuff. It's, if you have like some other complex number z over here, z times e to the I theta is actually rotating z. If like this were z, it's rotating z by some angle theta, and getting a new, say, z1 over here, and this angle it subtends, this rotation is theta. So that's actually what this e to the I theta does. Now in our case where we have the real axis here, the imaginary axis here, e to the I0, e to the I times 0 is basically rotation of 0 degrees. So this 1 basically rotates by 0 degrees, or is just 1. This is like the starting point of your vector, you can say, or your complex number, if you want to represent that as a vector. And since it subtends an angle of 0 degrees at the start, it's just this 1 on the real axis. But when we have e to the 2 pi I, that means a rotation of 2 pi. Rotation of 2 pi is like a complete circle on this. So what we're doing is actually looping back to this 1. So it's like we start with 1, we go in a circle and then come back to that 1. That's actually what's happening here. So it's actually important to see the complete picture, because people might make this error, and then they might be well, this integral's 0, so trivial, I mean, why did we waste our time? But this is actually a really good instance of how using the complex plane can help us see the greater picture here. So here, if you call this 1, our integral is basically a closed integral. It's an anti-clockwise closed integral, and this anti-clockwise clockwise will make more sense when we deal with I2, because then the direction is important for that, the convention. So it's basically a closed integral. I mean, if you want to denote this as anti-clockwise, you can draw arrows like this, but it's basically a closed integral that way. So that's what I wanted to show. Instead of having this I1 like this, we can show this in terms of a closed integral, and then we can make greater sense of it. Okay, so now that we know that this is a closed integral, let's write I1 as minus I over 2 times closed integral of e to the w over w times cosine of, we can write this as negative 5i times natural log of w dw. Now again, noticing the natural log, this is actually a hint to use the exponential definition again of the cosine, because the exponential and natural log are actually inverse functions of each other. So when we do that, we have e to the w over w, and then this will become e to the I times whatever was inside, so negative 5i natural log of w plus e to the negative I times negative 5i times natural log of w over 2 dw. Okay, all right. Okay, so now we have minus I over 2 in closed integral e to the w over w, and this will just be e to the 5 times natural log of w plus e to the negative 5 times natural log of w over 2, because I squared is negative 1. Okay, so now what I'm going to do is I'm going to use some natural log properties, some log properties on this exponential. So with e to the natural log of w to the fifth. Instead of multiplying by a constant, I'm just going to raise the argument to the power of that using log properties, plus e to the natural log of w to the negative fifth power over 2 dw. Okay, take the 1 over 2 outside, so we have negative I over 2 times 2, which is 4, closed integral from e to the w over w. E to the natural log cancels out because they're inverse functions. We have w to the fifth plus w to the negative fifth dw, and then we can divide by this w in the denominator. We have e to the w, and then w to the fourth plus w to the negative 6. Simple power rule there. And then finally we can have positive powers in the numerator by taking the common denominator. We have e to the w times w to the 10 plus 1 divided by w to the 6 dw. Okay, fair enough. This is actually I1, but I mean, this question was asking for it, wasn't it? I mean, we had a complex plane, a closed integral, that too on a complex plane. And what does that call for? That's right, residue theorem. Residue theorem is like a deal package with contour integration, like we have here. This is a contour, right? It's closed. So with contour integration comes residue theorem. So let's actually calculate the residues of this expression on a fresh page. See you there. Okay, so this is basically what our I1 turned out to be. And for residue theorem, we actually need a picture of the contour as well. So the contour, we start with 1, go around anti-clockwise fashion. I mean, now this isn't a perfect circle, but I think you get the idea. This is the real axis. That's the imaginary axis. Yeah. Okay, so the residues are calculated at those singularities. And singularities are points where this function, let me define the function first. So f of z is basically the integrand of this thing, but write all the variable terms in terms of z to denote a complex variable. So e to the z times z to the 10th power plus 1 divided by z to the 6th. Okay, so where is it that this f of z is actually blowing up to infinity? Where is it undefined? Well, notice it's undefined when the denominator is 0, and that happens at z equals 0, or basically this center point, the very center point. And provided that the singularity lies inside our contour, and well, it does, right? It lies inside this unit circle over here that we have on the complex plane. So yes, then we can consider that, because otherwise if it like lay over here somewhere like at negative 2i or something, then we can exclude that. That's basically the essence of residue theorem. Now to calculate the residues, notice we have a simple pole of order 6 because of z to the 6th power. So for that, the residue of f of z at our point, which is say z equals 0, is given by 1 over order minus 1. So order is 6 minus 1 factorial times the limit as z goes to our residue point, our singularity point, which is 0. Limit as z goes to 0 of, well, the n minus 1th derivative, and n is the order. So the 5th derivative, d sub 5 of z to the 6 time f of z. Okay, so this means we have 1 over 5 factorial limit as z goes to 0, 5th derivative of z to the 6 times e to the z to the 10 plus 1 divided by z to the 6. Z to the 6's will cancel out. But the problem is we still need to differentiate this 5 times. And this is not like a simple function. We have to use the product rule. Just look at this thing. We have to like use the product rule. But again, don't worry. Let's do it with concentration. So our first derivative turns out to be e to the z to the 10 plus 10 e to the z to the 9 plus e to the z. Second derivative, or differentiating the first derivative once again, e to the z to the 10 plus 20 e to the z to the 9 plus 90 z to the 8 e to the z plus e to the z. Third derivative, e to the z to the 10 plus 30 z to the 9 e to the z plus 270 z to the 8 e to the z plus 720 z to the 7 e to the z plus e to the z. And you may notice I'm already tired at this point. So d4 is some junk, d5 is also some junk, and we have to end at d5, the fifth derivative. But notice the pattern here. We always have some junk, which is a combination of the exponential and a polynomial, and we always end with an e to the z. I mean, doesn't matter how long the junk in between is, but we always end with an e to the z. And this junk is polynomial multiplied with exponential. Okay, fair enough. So we have this general structure for the fifth derivative. Now we have to take the limit as z goes to 0. So it's basically plugging in z equals 0 here. So notice that we have a polynomial times exponential. So if you raise an exponential to a 0th power, that will be 1. Okay, that didn't do much. But notice, if you plug in 0 in a polynomial, 0 to any power will always be 0, which will make the entire product go to 0. So all these terms over here similar. So d sub 5 will have similar terms like this. All these products of polynomials and exponentials will go to 0, except this last term over here, which will be 1, because e to the 0 is 1. So this entire thing is just 1. So we have 1 over 5 factorial times 1. So 1 over 5 factorial, that's the residue. 5 factorial is 120, 1 over 120. That's the residue that we need to care about. And why is the residue so bloody important? Well, that's because the closed integral of f of z dz is actually equal to 2 pi I times the sum of residues enclosed inside the contour. In this case, the only residue we have is 1 over 120. So sum of residues is 1 over 120. So 2 pi I times 1 over 120. That will be I pi over 60, and that's the closed integral we have. And that's exactly this part, this inner part over here. So to obtain an expression for I1, we still need to multiply by negative I over 4. I pi over 60. Because this closed integral was exactly this thing, right? Because the inner thing is f of z, except we change the w's to z's. So now minus I squared is going to be 1. So we have pi over 240. That's I1. Okay, that was easier. I mean, that wasn't so bad, right? Okay, now let's move on to I2. See you on the fresh page. Okay, so as pointed out on the very first page, I2 is actually half of integral from 0 to 2 pi of e to the negative ix times cosine of 5x dx. Okay, so now we're going to use actually a similar substitution like we did for I1. So let y now equal to this exponential e to the negative ix. So taking the natural log, we have uh, negative ix is equal to natural log of y, dividing by uh, negative I, we have x is equal to I times natural log of y. So that means dx is I over y dy. Okay, so we have half e to the y cosine of x is I times natural log of y. Dx is, well, take the I outside, divide by y dy. And when you plug in 0, you'll have e to the 0, which is 1, and e to the negative 2 pi I, which will also be 1. You can use the cosine of x plus I sine of x to check it. In this case, it will be negative I sine f because we have e to the negative ix. But in any case, this will still be 1. But again, like my previous I1, this is not like a regular calc 1 calc 2 integral. This is an integral over the complex plane. So you start with 1, you go around, you end with 1. But now here's a catch. Here's a catch. This was I1, right? This was the anti-clockwise version was I1, right? This anti-clockwise version was I1. This was I1. But I2 now is actually the clockwise version of this. So arrows pointing in the opposite directions. And you may ask, how do I know this? That's because look at this exponential, it's e to the negative ix. So if we have e to the I theta and some complex number z, giving us say z1, this expression means that you're rotating z in an anti-clockwise manner by an angle of theta, and then you end up with a new complex number z1. But if you have z times e to the negative I theta is equal to say z2, that means you're rotating z again by theta but in the clockwise direction, this way. So you're subtending like negative angles over here. Here you subtend positive angles, here you subtend negative angles because of this negative I theta in the exponential. And that's actually what makes the entire difference, because integrals in a clockwise order are always negative, and integrals in taken in the anti-clockwise are always positive. So one way that we can convert this clockwise integral into anti-clockwise is actually multiply by a negative. That is like actually exchanging the upper and lower bound. So like in regular calculus, we had integral from say a to b of some f of x, and if you multiplied by a negative, you couldn't flip the orders, right, from b to a f of x. So basically changing the orientation of integration, going from clockwise to anti-clockwise, you essentially do the same. You multiply by a negative. And we are doing this because by convention positive integrals are favored, and believe me, residue theorem and contour integration work best. I mean, the entire basis of residue theorem and contour integration to work is if the if the contour integration happens in an anti-clockwise sense. So for that to happen, we take a negative I over 2 and then have a closed integral, which is anti-clockwise, because we took the negative to convert to change the direction, e to the y over y. Now use the exponential definition of this cosine. So e to the I, phi I times natural log of y, plus e to the negative I, 5I natural log of y, 2 and a dy. Take the 2 outside, negative I over 4, closed integral of e to the y over y, e to the negative 5 natural log of y plus e to the 5 natural log of y dy. And like I1, I mean all these steps are actually a repetition of I1. We have y to the negative fifth plus y to the positive fifth dy. We can write this again with a y to the negative 6 plus y to the fourth dy. Now choosing positive powers in the numerator, we will have y to the 10th plus 1 divided by y to the 6th, if I'm not wrong, dy, which is essentially I1. This is essentially, this is exactly I1 actually. I mean, I'm just feeding you with a silver spoon now, I'm just, just got it in the right form of I1. And what was I1? Well, previously we found that I1 was pi over 240, and that's exactly this. We don't even need to do residue theorem again. That's excellent, right? Brilliant. But do you know what that means? That means like we are like really done with our problem. So our problem I was actually a sum of I1 and I2, and we both know that uh, we know that I1 and I2 were pi over 240 and pi over 240. You sum them up with simple algebra, you have pi over 120. And that's actually your answer. And if you want me to approximate, this is 0.026179938 approximation. So finally, I, which was defined as integral from 0 to 2 pi of e to the cosine of x, cosine of sine of x times, cosine of 5x dx just turned out to be pi over 120. And I think now we can generalize this. See, I naught integral from 0 to 2 pi of e to the cosine of x, cosine of sine of x times cosine of say some constant, I don't know, r of x dx will just be pi over r factorial, or if you want to generalize for all non-integral numbers, gamma of r plus 1. So yeah guys, I think that's it for this video. So please like, share and subscribe to my channel as always. Recommend me to your friends in the math community or anywhere else who might be interested. Keep doing math, stay home, stay safe, peace out. And one brief announcement before going. If you have like any real suggestions, if you don't like something in my video, if you like something, or I don't know, if you just want to voice your opinion, if you're bored in lockdown, you can always comment down in the comment section. And if I make some errors, you can point them out. I'll be glad to accept all your suggestions. So that's it. Peace out.